This is lecture 41. This is the first lecture in module 5, which deals with stochastic differential equation. So in this lecture, I'm just going to give you a basic introduction to stochastic differential equations, give you some examples of where you might see stochastic differential equations, and some examples of actual stochastic differential equations. Okay, so one example is money market versus stock. So consider a money market account versus a stock account. If you're thinking about a money market account, the thing that's interesting about a money market account, or that defines a money market account, is that it has a fixed interest rate, let's say R. So it's basically considered to be a riskless asset and can be modified can be modeled really well by an ordinary differential equation such as this one here. So the change in m with respect to time is just some constant rate r times m. So here this is just a regular ODE, a very simple ODE to solve, and you get the solution that the amount of money in a money market account at any time is given by the initial amount times e to the RT, where here r is a fixed rate. Another way that we can actually write this ODE is instead, so here we have the dm dt is equal to rm, and so I'm going to rewrite this, so I bring the dt over here, and I have the change in m is equal to rm times the change in t. And the reason why I'm going to write it like this is because you're going to be able to see the difference between a stochastic differential equation and an ordinary differential equation a lot better when it's written in this type of format. Okay, so on the other side, instead of money market was this riskless asset. So now consider stock here. If we look at stock, there is not a fixed rate. So the rate may sometimes be high, the rate may sometimes be low, and maybe even sometimes be negative. So the traditional stock is not modeled with an ODE, but it's actually modeled typically with a stochastic differential equation. And so this is the way that you typically see the model for stock is the change in the stock with respect to time is equal to some fixed rate here. So this kind of looks like our ODE. So if we go back up and look at our previous slide, so here, down here at the bottom, we had the change in m is equal to some rate r times m dt. Well, now if we go back here to the stock, what we see is we have, that is part of our equation, is we have the change in s is some fixed number here times our stock dt. But it also has this part here, which is actually what's called, the W is called a Wiener process or Brownian motion. And basically this is the part that adds the uncertainty into the model. And we're going to talk about a Wiener process. So if I say Wiener process or I say Brownian motion, basically in this entire module, they're interchangeable. So some people call it a Wiener process, some people call it Brownian motion. It's the same thing. Okay, so another example is logistic growth. So one of the common examples that you see in an ordinary differential equation class or even in a Calc 1 class is exponential growth. And logistic growth is similar in which you have the growth of a population, but here you're assuming that it can't just grow exponentially, that there's some limiting population, some reason for there to be a limit, so there's a maximum population that it can reach. And basically the differential equation that corresponds to this is dp dt, so the change in our population with respect to time, is equal to some rate times p, 1 minus p over k, where here k is that limiting population. The other way of writing this is basically bringing the dt over. So remember I said lots of times we want to write our ODE like this because then we can kind of see that this is going to be similar to our stochastic differential equation. This kind of gives us the average what's going to happen, and then we're going to add this stochastic term over here. So one way to add randomness into the model is again take this typical response with our ODEs. So think about this as the expected, what you have. So the ODEs tend to be thought of as the expected value, what you expect to have happen on average. But because things don't always happen that the way in a very nice fashion, you can add this stochastic term here, so the sigma p dw, and again the w stands for the Wiener process or Brownian motion. Okay, so an example of a stochastic model for spider movement. Now this is an example that I actually showed you in the very first lecture. So spider movement, I showed you a couple of videos. I'm not going to go through the videos again, but I showed you a couple of videos in which the movement of a spider towards a prey in a web is definitely stochastic in nature, and this has been modeled by myself and a couple of undergrads that I've worked with, and some people from the biology department. So basically here you can think about the change in the position is equal to some average position. So this is some kind of directional component with respect to time, and times the change in time, times this term that has this W here, which is that Brownian motion. So it's not going to go, so think about walking to class every day. So if you walk to class every day, you're going to take the same average path typically, unless you've got something kind of crazy going on. But like if you're just going from one class to another, you're going to take the same typical path, but you probably aren't going to walk in the exact same footsteps. You're going to have some variation about that. So this is kind of the average path that you would take, and this is that variation about that. And so here, this is just some kind of scaling factor, and this W again is the Wiener process or Brownian motion. Okay, so here's some examples of what that actually looks like. So the green is an actual spider, the blue is a prey, and then these are different paths that our model shows that the spider could have taken, because, you know, yes, the spider might have taken this one in the video that we used, but will it always take that one? Probably not. But these paths were chosen, so about the same amount of time is taken to get from the starting location to the ending location. And about the same amount of time and the same distance has been traveled, basically. So again, here, if the spider's starting here and it's heading down here, you have variation, but the average amount of time that it takes to get from here to here is about the same. It just is not going to take the exact same path every single time, and again, you see it here. Okay, so another example of stochastic differential equation, or where it might be used, is climate variability. So there's a model that was written about by Vallis, or developed by Vallis, and it's a simplified model which models the interaction between the atmosphere and the ocean's surface. So here they let capital T with the superscript A stand for the atmosphere temperatures, and the capital T superscript S, and then for the sea temperatures at the same time little t. And so here they model this equation here, in that the change in the temperature here at the surface is going to be a result of the change of the temperature here in the atmosphere and the temperature at the surface. And similarly, what you have is the change in the atmosphere is going to have the things that are going to affect the change in the temperature of the atmosphere is going to be the temperature at the surface, the temperature at the atmosphere, and then some kind of stochastic terms, so random fluctuations. So there's always random fluctuations when you're talking about the temperature of the atmosphere, and so the sigma BT stands for that kind of random fluctuations. And so we've been using W. In this paper, uses B to stand for the Brownian motion. Okay, and so this is a couple of examples of depending upon, so here you have this sigma term. Depending upon the sigma that you get, these are different variations as to what might happen and how, and this is the ODE is the smooth curve, and kind of like you saw in that first assignment that you did at the very beginning of the semester, you have variation about your ODE system, and then you have more variation depending upon what your sigma is. And so these are three different kind of sample paths for the stochastic differential equation. Okay, so next time we're going to define what the Brownian motion is, or the Wiener process is, in a little bit more in a more refined way, a more formal definition of what Brownian motion is. But the basic concept is the Brownian motion or the Wiener process as this randomness or stochasticity to a model.